Okay, so welcome back, everybody. So it's a pleasure to introduce Lucas Reis from the Universidad Federal de Minas Gerais, and he will talk about counting digraphs from linear finite dynamical systems. Please.
Okay, can you hear me? Okay. So this talk is about a counting problem in on digraphs over finite sets. So first I'll just start with the concept of finite dynamical systems. So basically we have a finite set, X, and then a map from X to itself. Since the map is from X to itself, we can make iterations, right? And discuss like classical questions in dynamical systems, right? So we can ask about the behavior of orbits and purely periodic points, etc. It turns out that in the case of finite sets, we can associate the map to a digraph, and many information of the map can be extracted from this graph. So the idea is that the digraph just tells you what the function is doing. So we have a directed graph with vertex set is the set X, right? So I'm labeling the vertices with the elements of X. And then I have directed edges from X to Y if Y is the image of X by the function. Okay, so here is an example. For instance, we can consider this map, right? A goes to 2 times A mod 28, right? So this is the graph we get. It has 3 connected components, and we have like some sort of symmetry here on each component. Also, we have this example. So I consider the map A goes to A squared plus 1 over Z12, right? So for instance, here I have the element 6. It goes to 1, and then 2, and then 5, and then enters this cycle, right? So it goes 5, 2, and so on. Okay, some remarks about the graph. We can relate the map, and we can get information from the map just looking at the graph. For instance, if I take any element at the domain x, little x, the forward orbit, right, so I'm taking iterations of this map at the point x, it can be described by the largest path in a graph starting from the vertex x. And also the purely periodic points. Yes?
Do you have a fixed point you add a loop?
Yeah, exactly. It's in this next comment, right? So purely periodic points, I mean just a point after some iterations returns to the original input, right? So they are just described by what we call cyclic graphs in the graph. And in particular, fixed points would correspond to loops. This is a sort of active topic of research. And if I'm not wrong, it started, like the main motivation is a method of factoring integers. And they basically use like a family of quadratic maps to draw the graph, and then when we have like two vertices going to the same vertex, we basically get some sort of partial factorization of the integer. So it has some applications, but here I will just comment on the what has been done is mostly theoretical, right? We have this motivation, but most of the problems are purely theoretical. And the main problem, of course, is to describe the graph, right? So if I give you the function and the set, I want to describe the graph. Of course, without going through edge by edge, right? So I want to see just a picture without building the entire graph. And here I'll just comment on some past work. So this is in general a hard problem because essentially a very generic digraph can be the graph of a function over a set, right? So most of the works, they focus on finite sets with some algebraic structure, and the map has nice behavior with respect to this structure. So here are some examples. So for instance, if we consider finite groups, we have like power functions, right? So I can consider the power map G goes to G to the n over an arbitrary group. We also have like this very specific rational map over finite fields of characteristics 2, 3, and 5. Also, Reis functions and Chebyshev maps over finite fields. Some maps, rational maps arising from endomorphisms of elliptic curves over finite fields, and also linear maps. And in fact, as I was saying, right, this is in general a hard problem. And basically in all of these cases, the graphs will have like lots of symmetry. So there is a natural reason for why we can describe the structure of the graph. And in fact, in 2019, joint work with Claudio Kuresh, we basically unified most of the past works in a very general setting, explaining why we get these symmetries on the graphs. And basically what happens by symmetry, I mean, each connected component will just be of this form. So we have like a cyclic graph here. And then from each graph we hang a tree, but basically the same tree from each vertex. Now I'll just give some comments on the case when X is a finite field. So if we think like we take an arbitrary map from FQ to itself, is a finite set, and it is also a field, right? So if we apply Lagrange interpolation, any map is polynomial, right? So this is why like discussing polynomial maps is already hard, because it can be any function from the set FQ, right? And here is a survey for those who are interested. Like, there are many discussions on progress of this subject in the finite field setting. Okay, so, but this talk is about counting problem, right? So one question that, well, at least I find natural is now we take like not just one map, but a family of maps, right? So they are similar, so they're in some sort of way they behave in the same way. We can ask about like enumerating problems, right? So we start with a family of functions, and then we draw the graphs, and then we can ask like how many distinct graphs can we get as we run this function over this family, right? And by distinct here, I just mean non-isomorphic. So I'm just looking at the picture, not as a graph, right? So the graphs can be distinct, but the picture will just look the same. And this actually has an interesting meaning for functional graphs. So a graph that is like just encoding the information of a function. And I just recall what is, yes?
What is the algebraic structure X in?
Well, it can be a group, a field, a ring. Yeah, we can, you can choose, right? And so you take the map accordingly according to your set. Okay, any more questions? Okay. And so I'm just recalling here the definition of isomorphism of digraphs, right? So it's just a bijection between the vertex set, which preserves the directions of the edges, right? So, and basically in the case of functional graphs, so if I take the functional graphs of two functions over two sets, we basically get that this corresponds to a conjugation between the two maps, right? So if I look at the same graphs, this is the same thing as saying that the functions are conjugated by a bijection between two sets. So for instance, if my set X is fixed, is a conjugation by a permutation of the elements of X, right? So here's an example. It's not like the main topic of this talk, but for instance, we can consider the family of all quadratic maps over finite fields. So in particular, if my characteristic is odd, it's not 2, this is always conjugated to x squared plus a, right? And it has like it's natural to consider this problem because over the complex setting, this is a very well-studied object. And so basically, I'm looking for quadratic maps, so the leading coefficient is non-zero. So basically, I get around Q cube maps, but we can already reduce these to Q, right? So I have Q cube maps, but when I look at the digraphs, I have at most Q not looking like each other, right? And here there is a work giving a lower bound for the number of pairwise non-isomorphic graphs we get from quadratic maps. So we know that this is at most Q, but we can also prove that this is at least a constant time Q's to 1/4. And I'll just briefly explain the proof behind. This is very nice because there is some combinatorics. Yes? Sorry? All the quadratic, right? So you get x squared plus c. C is varying over the field of Q elements. So we get at most Q, but we can also prove that we get at least C times Q to 1/4. And so basically the idea is that, well, if I consider a map like this, x goes to x squared plus c, I basically have like two situations. So if I take a vertex A, right, I either have like two pre-images, right? So in this case, this is basically saying that A minus C is a square of my field, and otherwise I have no vertices directing to A, right? And there is one exception. There is the map C that always has a 0 and only 0 as a pre-image, right? Of course, we have like a double root of the corresponding polynomial. And so the main idea in this paper is just to consider two maps, F, x goes to x squared plus a, and G, x goes to x squared plus b, and provide like necessary conditions for these two maps to be conjugated, right? And the key point is to look at this very unique point in a graph, the unique vertex, which has only one pre-image, right? So this happens only once in a graph. So if I have an isomorphism between the two graphs, they have to be mapped to each other, right? So here I would just have like 0, and then f of 0, and so on, fk of 0. And then I do the same thing with G. I have here 0, G of 0, and so on to gk of 0, right? And so basically these two, I'll have here G squared 0, and I also have here minus G0, right? So each element here we have the minus, the element will be a vertex towards this vertex. And here, so I have like minus F0, etc., right? And so I basically look at this picture, right? So I have here minus G0, minus G to 0, etc., to GK0 minus G K minus 1, 0. And the same picture for the map F, right? And so basically now we have this shape in a graph. And now I can either have like 2 vertices towards this or none, right? So for each vertex here, I will have these 2 choices. And basically, if I make one choice for A and another choice for B, they're not like the same. The graphs cannot be isomorphic already, right? So we don't need to work with the whole graph and just this sequence. And so basically, the idea is to now giving the map F, let's say, I'll just pick the values of these guys, right? So minus F0, minus F squared 0, and so on. And then basically I pick the sign, right? So I can choose that this vertex is of this type or this type. So this is just like a quadratic condition. This is a square or not, right? And basically this can be, so if I make like a choice of signs here, let's say plus if it has 2 guys, minus if it doesn't have 2 guys, etc. This can be encoded as some sort of characteristic function. So I try to, like for a choice of a sequence of signs, I can get like it would be something like this. This is basically the Legendre symbol for the function. And then I get plus or minus 1, and we have to divide here by a constant. I don't want to get into the details, but basically here I would put, I can exchange F0 by A, right? So it's a parameter here. So at the end we basically get something like this, and we are choosing the parameters here, right? So basically what we want to prove is that we can freely prescribe signs here. K cannot be too large, so we have some limitation, but at the end, if we prove that this is positive, it means that we can choose the signs freely, right? And at the end, well, we can prove that this is positive using Weyls bound on the number of rational points on certain curve, and as long as K is, I think is about a quarter of log 2 Q plus little 1 of 1. And so basically, we can choose, we have like 2 to the K choices for the sequences of signs, and then we can get the C times Q to 1/4. Okay.
It's difficult to find the asymptotic
Oh, you mean to write asymptotic? Because this is a lower bound, right? We have the upper bound Q.
Because one doesn't even probably know that there is an asymptotic.
Yes, yes. But I think I haven't seen this in any paper. Like, I have one guess that this will go like Q over log Q. But yeah. And basically they did like it's a very smart idea, and the best they could get it was 1/4, right? So this is pretty far from Q, right? So we don't know the right growth of this function. Okay. But this talk is about linear maps, right? So we focus here on linear maps over finite vector spaces. So here my set X now is FQ to the n, right? So it's the set of vectors with any entries in FQ. And my family of sets here will be the set of all FQ linear maps over this set. And then I call NQN the number of distinct digraphs I get as I run over all the linear maps. And just a comment here, because I say about Lagrange interpolation, right? We have a one-to-one correspondence between maps and polynomials, modulo x to the q to the n. And basically, the linear maps they correspond to polynomials of this form, which we call q additive, right? So each monomial appearing will have like degree, a power of q. Okay, so here's one example. I consider this linear map from F to 6 to itself, given by this matrix, right? So you can think like I fix any basis for this vector space, and I consider the matrix associated to this map, right? And here we get the digraph. It has only one component, right? So here we have 0, which is a fixed point, and basically we can think this example is very relevant because we can see that this map is nilpotent, right? So we have like Jordan blocks associated to the eigenvalue 0. And basically for a nilpotent map, it would look like a tree, right? So because if I take any point and I iterate, I eventually get to 0, which is the unique fixed point of this map. Okay, so first we get like a very trivial bound, right? Of course, I get exactly q to the n square maps because this is the number of n by n matrices. And so in particular, I get this lower upper bound, right, for this function. So we are not studying nqn as we're taking a double logarithm because this is what we can do to study the growth of this function, right? So if I quotient this by log n, the lim sup is at most 2, right? So here is an improvement from 2013. Back in Brady, they proved that the lim if is at least half and the lim sup is at most 1, right? And so basically, our result here is that the limit actually exists and it's equal to 1, right? So the lim if is a bit far from the actual limit. Okay. And just one comment about this result. Well, it's almost an exercise to prove that the number of conjugacy classes in the general linear group satisfies this growth, right? So log of CQN grows like log n, right? So of course I can identify the invertible n by n matrices with the linear maps that are bijective, right? And so just one comment, I would go into the details, but the lower bound here to achieve this limit is actually just considering bijective linear maps. So if I take nq and replace by the function just counting bijective, I just get the same limit. And so in particular, if since I'm looking for the non-equivalent graphs, this means that I'm just considering bijections up to a permutation of the vector space, not necessarily a linear bijection, right? So here we have two groups, right? I have GL and Q, and then the set of all bijections of FQ to the n to itself, right? So I have two groups here. And this is basically saying that the number of conjugacy classes doesn't change much, even though the group is way larger, right? So SQ to the n will have Q to the n factorial elements, which is way larger than the size of GL QN. But when we look at the conjugacy classes of bijective linear maps, they will basically grow in the same way. Okay. So now I would, for the rest of the talk, I'll just give some ideas of how to get to this limit. There will be some number theory at the end. But first, I'll just define here what is the product of graphs, right? So I take two directed graphs. I can define their product, right? So the product now has a vertex set just corresponding to the Cartesian product of the vertices of G and H, and the edge set just follow the edges in H graph, right? So a pair GH of vertices in G and H will go to G prime, H prime, if and only if G goes to G prime and H goes to H prime. And here is an example, it's the only relevant example we need for the talk. is when we take the product of a cycle times a tree, right? So for instance, here I can have like a cycle of length 2, and then I have a tree. Well, a called tree is not really a tree because it has a loop at the root, but for simplicity, I'm just calling a tree. And basically, when we tensor these two graphs, like a cycle and a tree, I basically get a graph which is a cycle, and at each cycle, I just attach a copy of this tree, right? So this product here would just look like this. I have this and this. Is that clear? Well, it's just a very simple induction. Yeah, there are many proofs that this happens. If I tensor a tree with a cycle, I just get something like this. Well, and this product is relevant when we are considering maps because they behave well when I take the product of two functions, right? So if I have two maps, f over x and g over y, I can consider the product function, right? So I map first coordinate I go as f, and then the second one as g. And the digraphs, corresponding digraphs, will behave well, right? So the digraph of the product of the functions is isomorphic to the product of the graphs of each function. Okay. So now basically the idea of estimating this number, so I'm taking like considering all the linear maps over this vector space, fq to the n. We actually just go through the most standard linear algebra approach, right? So I'm trying to reduce this map, look at some invariant subspaces where the map will look friendly, right? It turns out that these graphs will have this nice symmetry. So it is comprised by cycles, where at each cycle I have a hanging tree. They're all pairwise isomorphic, right? And here's basically the explanation. Of course, I can decompose my space into T-invariant subspaces where at one component this map is nilpotent, just corresponds to the eigenspace related to the eigenvalue 0. And the other is just a complement, right, with respect to this map, or to this decomposition. And in this case, what remains after the nilpotent part is just a bijection, right? So V0 will be responsible for the tree, and V1 is responsible for the cycles. And at the end, I just have to tensor, right? Because if I decompose my space, this is important. If I decompose my space into two invariant subspaces, I can see the map as a product of maps, just considering the restrictions to each of the invariant subspaces. Okay. And now it turns out that if I take this decomposition for two maps, so T and S, I have two subspaces, V0, U0, V1, U1. It's natural to, well, it's not hard to prove, but I mean, it's natural to expect that they are conjugated if and only if these restrictions will be conjugated, right? Because one is responsible for the trees and the other one for the cycles. Okay, so basically with this result, right? So the isomorphism class of the digraph is uniquely determined by the isomorphism class of the trees, of the tree and the cycles attached to the map. We get this convolution formula, right? So if I want to count digraphs, I just need to count all the possible pairs of trees and cycles I can get as I run over the possible decompositions of the dimensions of my space. And actually, in the case of nilpotent maps, so now I'll just try to estimate nil Q and BQ, right? Bijective and nilpotent maps. And it turns out that for nilpotent maps, they will be conjugated if and only if they are linearly conjugated, right? So their conjugacy classes, let's say, they don't change actually. And for nilpotent maps, well, they have the same, they will be conjugated if and only if they have the same block distribution when we consider the eigenvalue 0. And so now, at the end, we just get the number of non-isomorphic trees I get for n minus k dimensional vector space is just the number of ways of writing n minus k as a sum of positive integers, the order not being relevant, right? So it's just we get here the partition function. And basically we know how the partition function grows, right? So it goes like exponential of c times the square root of t. And in particular, looking at this formula here, we get this lower bound, right? So the number of distinct digraphs is at least the number of distinct trees. And the number of distinct trees is about this number, right? So we can actually recover the limit that was proven by the other two authors, right? It's interesting because the proof of this limit, they actually only consider bijective linear maps. So we actually work with the complement of this situation. Okay, so basically most of the work will be on the function bqk, which is way more complicated. And actually, this is what matters, right? We have that the function nu q behave like an exponential of a square root, and basically the bq dominates this term. So, in other words, actually we can obtain nqn is basically bqn, right? All the other terms will be very irrelevant to this sum. But the problem with bijective linear maps, they are more complicated. In fact, for nilpotent maps, we can even, the trees will have a very nice structure, and we just have to look at the size of the Jordan blocks appearing. But for bijective linear maps, things are more complicated. Because we don't have this result, right? So we might have like two bijective linear maps. They are conjugated by a function, but not necessarily by a linear function, right? So I just brought here one example. I can consider this map, multiplication by 3 and multiplication by 4 over F11. These two maps will have the same graph, but they are not linearly conjugated, right? So if we look at the matrices, of course, they're not like conjugated by another matrix. Okay. So now I just need one more thing. I denote by psych n as the cyclic graph, directed graph with any n nodes, right? So for instance here, this is psych 2, right? And they behave very nicely through the tensor product, right? So if I have a cycle of length n and a cycle of length m, and I take the product, this splits in many copies of a graph, a cyclic graph of length, the LCM of the two numbers, and the number of copies is just the GCD. Okay. So now focusing on the bijective part, what we do is to break the space again into invariant subspaces, right? So here I have a bijection, and I want to decompose in very nice invariant subspaces. So we have this theorem, which is called the rational form, right? So it's basically a generalization of Jordan form for fields that are not algebraically closed, right? So basically we can, if I take a bijection here, I can decompose my space into invariant subspace that I'm calling minimal. And they must have two properties. So first, the characteristic and minimal polynomial of this map, linear map, coincide, and also they're equal to a power of an irreducible polynomial. So that's why the minimal comes from this power of irreducible. And it turns out that for these maps, if I take the restriction to a minimal invariant subspace, we have a very nice description of the graph, right? So basically, I'll have one fixed point, which corresponds to 0. So I have here one loop, and then some cycles of length L for some L. And then all the other cycles appearing, we have like L, we have length L times the power of P, right? So I'm basically just increasing the length by a factor of P. And moreover, L is, we only have one restriction here. If my space has dimension, if my polynomial has degree k, my number L here must be a primitive divisor of q to the k minus 1, which means that it divides the number q to the k minus 1, but not another number of this form with a smaller exponent. And also, well, the number of times that each cycle will appear and the size of the largest cycle, which will be L times the power of P, they only depend on L and S, right? So only the multiplicity of the polynomial. And this number L, I will not explain what is this number, but once we get F, we can compute L. Okay. So in particular, we can see that if I determine L, S, and the degree of F, I have the graph, right? So it doesn't matter what is the map. I just need these three data. And this actually gives a key to determine an upper bound. And I'll skip the details and just explain what we do. And basically, I'm trying to give three parameters, right? So L, S, and the degree of F. If I give the degree and S, I have the degree of F to the S, right? So I have the dimension of my subspace, right? So what I would do now is just to choose the dimension first. So I fix the dimension as a number k, and I already tied S and degree of F by an equality, right? So second, I just pick the number L, so I have a choice for L, and basically L will determine the degree of the polynomial. So I won't explain the details on that, but once I get L, I get the degree, and then I get S. And the only restriction at the end I will have is that L must be a divisor of q to the k minus 1. And then, of course, we arrive at there is like a binomial coefficient appearing here, and basically, I just have to choose the number k's, right? How many times k appears, and I have to sum all of them sum up to n, which is the dimension of my original space, right? So basically, I'm taking partitions of my number n, so I decide the invariant subspaces. I choose the L's, and then I get the graph, right? So at the end, we get this upper bound, right? So BQN is at most this size, right? How much time do I have?
I think still 10 minutes.
10 minutes, okay, great. Okay, so we basically get this upper bound, right? So here, sigma j is the number of divisor of q to the j minus 1. And basically, we have a result here from Robin giving an upper bound for the number of divisors of q to the j minus 1. And then, using this inequality, we can get this upper bound, right? So lim sup of this quotient is at most 1. Okay, so now for the lower bound is more complicated because basically we have like, if I consider each minimal invariant subspace, I'll have something like this, right? So a loop and then some cycles of length n, L, and then cycles of size of length L times the power of P, right? So basically if I have at least 3 different cycle lengths, when I tensor these, it can become much more complicated, right? So we have like many possibilities of all combinations, and this makes everything harder to compare, right? Because I will basically now take 2 maps and compare these products of cycles and try to get some conclusion, right? But the point is that cycles of size, the characteristic of the field times something, only appear if I take greater than 1, right? So if the minimal subspace is related to a polynomial with the irreducible factor has some multiplicity, right? So the idea, and basically this is the key of all the paper, is to only restrict to maps whose characteristic polynomials are square-free, right? So when I take this invariant minimal subspaces, the exponent is just 1, and I get rid of this mess I get when I have the cycle decomposition, right? So for these maps, I'll just have these, right? So I have the loop and then copies of the graph of the same length, right? And basically now what I do is the following, right? I break my space into minimal invariant subspaces, all having this property, right? So now the characteristic polynomial will be reducible for each minimal component. And then for each component, I have a number L. I first carry all the L's that are equal, and I gather them together. So I would tensor things of this type with the same L. And then by this GCD LCM rule, I get, again, a graph of this form, right? So if I tensor cycle 1, cycle L, I get cycle L. Cycle L, I get cycle L again, right? And basically, the idea is that when I decompose in this way, I have some sort of unique factorization of graphs, right? So if I take two digraphs, where in each component I have something like this, so it's a loop plus copies of the same cyclic graph, and then I ask in each component this number, L being different, right? So I can decompose a graph like this in a very unique way. So, right, I conclude that the number of connected terms here in this product is the same, the lengths are the same, and the copies are the same. Right? And just a remark, this is only true if I ask for the lengths to be pairwise distinct. Here's a counterexample, right? I have two ways of writing this graph. Okay, so basically with this theorem, we can conclude the following. So if I take two bijective linear maps with asking for requiring that the characteristic polynomial is square-free, they would eye out the same digraph if and only if the list of numbers L I get from each invariant subspace up to a permutation will be the same, right? And so basically now I just need to compute how many lists of L's I can get from a vector space of dimension n, right? And basically the idea is the same for the lower bound, but here there's only one catch because S is always equals 1 here. We are taking this restriction. So now the degree of my polynomial is necessarily K, the dimension of the space I choose. So in this case, we have one more restriction on the divisor L. It cannot be any divisor, but it has to be a primitive divisor of this number. So at the end, I basically get the lower bound really looking like the upper bound. If you recall here, the upper bound we got was this one, right? So we have this sigma of j, which is the number of divisor of q to the j minus 1. And now for the lower bound, we just get sigma j star, which is the number of primitive divisors of the number, right? And in particular, well, we have this weird sum. There are many partitions, etc. But we can see in particular that I can take a very smart partition. So I ask for the matrix will be basically distributed through blocks of size j, and then I just add something to make a dimension n, right? So I would take a very simple partition of n, right? So I write n as j times the floor function of n over j plus the error, right? And in particular, I can get this bound, right? So bqn is at least this number, right? So I only have to study the number of primitive divisors of one number, q to the j minus 1, and I have to choose J wisely. Okay, so here comes a bit of analysis, right? So we want to give a nice bound, so I need to find a nice lower bound for this binomial. The optimal choice would be having sigma j star close to lambda j, but the problem is that this function behaves really wild, right? So the number of divisors of q to the j minus 1 as j varies over the integers is actually a classical problem in number theory. There are some papers of Erdős studying this problem, and actually we don't have any, let's say, satisfying information on the number of divisors of numbers like this. And just to give a very interesting example, if we consider 2 to the j minus 1, right? So this number can have like many prime factors, but at the same time, we don't even know if this number is prime for infinitely many exponents, right? So basically, we cannot give like the exact growth of this binomial, right? So this is very, I think it's out of reach, right? And so basically the strategy, I'll skip the details. We just want to find sigma j star large enough. So if this number is big, we can get a nice lower bound for the binomial. And the idea here is that there is a theorem of Zygmundi's. Basically, the primitive divisors, so they divide with the exponent g, but not a smaller one, most of the divisors will have this property. So basically, I just need to find j such that q to the j minus 1 has many divisors. And here there is a very nice option. I just take j with many divisors, and to save up the growth of j, I just pick j as the product of the first primes. And well, basically there is the prime number theorem playing a role here. I have a choice of how many primes I want, and then I can get this ugly lower bound, but in particular, I can conclude that the log grows as this. Okay. So just to finish some future work, it will be interesting to see how relevant are the non-square free part, right? So if I have cycles of length divisible by the characteristic, if these affect a lot or not the problem. And secondly, just ideally we would study the growth of BQN, and then we went to log, we got the growth exactly. So the next step would just go to this just one log scale, right? So log of BQN. And basically the upper bound is this one. This was known since Brady and Ba. And then we will obtain it this lower bound, right? So it would be nice to get the exact growth of this function. Okay, I'll stop here. Thank you.